Hey everyone, welcome to the Drive Podcast. I'm your host, Peter Attia. Hey George, thank you so much for making time to sit down with me today. This has been a long time coming, as you know. Your colleague and partner in crime on much of the work you've done, Inigo San Milan, has been a multiple time guest on this podcast. And of course, your name has come up many times. I've referenced you and your work in my book. So it's great to be sitting down with you and to talk about lactic acid, which is something that I think I think it would be safe to say at the outset is probably a misunderstood molecule. Would that be a safe statement to start this out?
Yes, it is, and thank you, Peter, for having me on. You really helped make my career, because my physician wife's friends know my name, but after reading your book, they say, "That's George." So that's really great. So, not to be difficult, but you did mention lactic acid.
Yeah, I was just about to say, I'm glad you brought that up. I assume you're going to say, should we really think about this as lactate or lactic acid? And let's have you get the semantics right out of the gate for us.
We can say lactate.
Yeah.
The body does not make lactic acid.
Right. Makes lactate, and then there's a hydrogen ion, and presumably if there's a hydrogen ion near the lactate, it's lactic acid. Is that the...
That's been a historical mistake. It's 100-year mistake. It's like lactate is not just an innocent bystander. It's a participant in the process of powering muscle and, in fact, all cells.
So let's go back in time 100 years, right? Because it was about 100 years ago that Otto Meyerhoff made a seminal discovery. Can you tell us a little bit about what that was and how that sort of started a chain of understanding that brought us to where we are today?
Yeah, so the early 20th centuries, people were trying to unite what was known from fermentation technology to what was coming out of studies of muscle metabolism. And Meyerhoff was a great man, a great investigator, and one of the things he did was to quantify how much glycogen is in muscle and how when it degrades, it produces lactate, at that time thought to be lactic acid. So we're projecting now a picture of the seminal kind of experimental setup that Meyerhoff and colleagues used. And they had a half a frog in a jar without oxygen supplementation, without any perfusion, that is blood flow. And this half a frog, the muscles were made to contract, and they contracted until they couldn't contract anymore. And then quantitatively, Meyerhoff could say, well, there was X amount of glycogen and there was X amount of lactate produced. And so that was really instrumental in developing this pathway. But if you look at this is really not what we are. These muscles are made in nature to contract once or twice. The frog hops, it gets away or gets eaten. So the muscle is not representative of us. But in this situation, they stimulated the muscle to contract. It stimulated glycolysis to produce ATP. And at the end, the muscle fatigued. And at the end, there was a lot of lactate. And there was also a lot of acid. So this is how we came to associate lactate or lactic acid production and oxygen lack, because there was no oxygen around here, so it had to happen. It was a fait accompli. And this led to the idea of lactic acidosis and the anaerobic threshold and the oxygen debt. But if you just look at this simple apparatus where we have a half a frog made to contract, this is really the aegis of our understanding of how carbohydrate is used in the body. All textbooks, most textbooks, well, not mine, talk about glycolysis going to make pyruvate, and when there's no oxygen, lactic acid. So this has been a problem. And this spills over not only into muscle physiology, but it spills over into pulmonary medicine. It spills over into cardiology. It spills over into nutrition. Now we know a lot of things that were not known, could not be known at that time. And right now, I think I'm going to stop sharing the screen to talk more directly about our new research.
Well, I want to go back to that for a second, though, before we get there, George, to make sure everybody kind of understands the experiment and the interpretation. So again, some folks couldn't see that image, but basically you were showing a schematic of an experiment. So let's just kind of explain what was going on there and maybe try to understand the interpretation. So the musculature of part of a frog is put into an anaerobic chamber. This is a chamber that has no oxygen, and it's not perfused. So there was no blood to carry hemoglobin, to carry oxygen to the muscles. Presumably electrodes were placed somewhere on the musculature within the chamber, and the electrodes provided the stimulation for muscle contraction. And then the question became, what is it that fueled the contraction? Well, obviously it's the glycogen within the muscle, but if glycogen or glucose is being used to fuel contraction without oxygen, it somehow must be happening in the absence or exclusion of the mitochondria. And so what they were measuring was the consumption of glycogen, the production of lactate, and presumably they could measure the pH in the solution. And I'm assuming that the pH, which is a measure of acidity, was going down. Is that all correct?
That's all correct. That was the observation.
Okay. And so the interpretation of that observation was what at the time?
Well, first of all, that was important in terms of quantifying glycolytic pathway, precursor and product. You start with a certain amount of precursor, and you wind up with a certain amount of product. But since then, people have associated the appearance of lactate with oxygen lack.
Yep.
And that's a mistake. There was no oxygen there. And it's a stress-strain kind of relationship. The muscle is stressed to perform. It uses what it has. It uses glycogen. It produces lactate. And there's also an acidosis. So there's an association with lactate and lactic acid, acidosis and fatigue. So this whole thing was all boiled up in one knot. So when I learned exercise physiology, it was all those same things: fatigue, acidosis, lactic acid.
So George, in the experiment that Meyerhoff did almost exactly 100 years ago, at some point, I assume the frog's leg stopped contracting in the presence of the stimulus. And is it believed that that was due to a depletion of glycogen, or was it believed that the degree of acidosis had become so significant that the acidosis crippled in some way the actin and myosin filaments of the muscle and prevented either further contraction or relaxation?
Exactly. So at that time, people were trying to understand why muscles contracted. And it was just a simple kind of thing like, let's have tea. And would you like tea with cream, or would you like it with lemon? Oh, I would like it with both. So then you get this curdling, the acidosis. And so one idea of muscle contraction was that actually the actin and myosin kind of curdle, and then they have to uncurdle. So it was believed that the accumulation of acid, lactic acid, caused fatigue.
And when you look back at that experiment, and I'm going to jump around a little bit because there's a bit more history I want to get into, but just so people can understand how you think about this problem today based on the entirety of your work, what do you believe was the explanation for why the frog's muscles ceased to contract in the presence of an ongoing stimulus?
I think what happened was there was ATP and creatine phosphate depletion in this anaerobic environment.
Interesting. By the way, how much does, in an experiment of that nature, how much does the pH go down?
I don't think they reported the pH, but the pH would probably go just a bit under 7.
Got it. And just for folks listening who aren't familiar with pH, pH, the number, I guess, can be as low as, what, 1 and as high as 14? Is that effectively the range of pH, something like that?
That's right, yeah.
Although physiologically, I mean, that would be in a chemistry lab. Physiologically, in a mammal, it's very hard to get too much below the high 6s and too high above the high 7s. And the higher the number, the more basic, and the lower the number, the more acidic. But would you agree with that physiology tends to exist in the 7s, with 7.4 being kind of perfectly neutral?
Yeah, so I'm teaching physiology now, 7.38, 7.4. And you're right, it's really hard to get the pH to 7 or even a little bit below.
Yeah, I'll tell you just a funny anecdote, maybe a not so funny anecdote, unfortunately, but a very common story. When I was training in surgery, obviously when trauma patients are brought into the trauma bay, one of the pieces of data that the paramedics have on the way in is the pH. They know they can measure blood pH very quickly and easily. And that became a way that we would triage readiness in the ICU and in the operating room. And so when gunshot wound victims or stab victims were being brought in, even if they were alive, if their pH was 7 or 6.9, we knew that it was very unlikely that they would survive, even if their heart was still beating at the moment that was reported to us. I can think of one case that was a miraculous case where a guy was brought in with a pH of 6.9 on arrival, and he managed to survive, which is kind of an amazing story. But it is funny how the body really, really regulates acid-base balance. So let's fast forward a little bit, George. So if I'm not mistaken, did Meyerhoff win the Nobel Prize for that observation in 1922?
Yeah, he was awarded it along with A.V. Hill. And A.V. Hill is a very famous name in physiology. We sometimes refer to him as the father of physiology, or the father of muscle physiology, or the father of exercise physiology. And so A.V. Hill and Otto Meyerhoff shared the Nobel Prize.
I don't remember exactly when Warburg made his seminal observation that also bears his name, but I'm guessing it was about 2 decades later. It was probably in the 1940s. Is that approximately right?
Otto Warburg was actually Meyerhoff's professor in Germany. And so you're talking about the Warburg effect, cancer cells. Yep. Cancer cells will take sugar, glucose, and make lactate. And they do that under fully aerobic conditions, under room air, where the oxygen is actually higher than it ever is in the body. And these cancer cells will just break down carbohydrate, break down glucose quantitatively, and you wind up with this lactate and acid. So we don't need to go out into any more than we have. But if you look at the glycolytic pathway, at the end there's pyruvate, anion, and a proton, and NADH, this redox carrier. It gives us lactate, anion, and NAD plus. So the last step in glycolysis does not make acid. It's actually an alkalizing step. But in metabolism, there's a lot of things that can give rise to acid. And some of the intermediates in the glycolytic pathway are acids. So there's lactate and there's acid. So your observations in the ICU, to be concerned about pH, of course, that's really important. That's essential. Sometimes people also measure lactate.
That's right.
Yeah. And for instance, in sepsis or other kinds of conditions, people will be measuring lactate. But I think you're making an important distinction between pH and lactate.
Yeah, I assume that because we would measure lactate all the time if we thought sepsis was brewing. But I suppose, and we'll get to this in more detail, that we were using lactate as a surrogate for something that was of greater concern to us, which was actually the pH balance, correct?
That's right. Yeah.
George, I want to go back to some fundamentals, and I was a little delinquent in not doing this out of the gate because I wanted to sort of jump right in. But it occurs to me as we're talking now that I don't want to take for granted that our listeners really might be as familiar as you and I are with metabolism and frankly, the breakdown of a carbohydrate into what ultimately becomes ATP. So I'd like for you to spend a moment explaining the following. So at a high level, this is what I will typically tell a patient if I'm talking about this, or if they express an interest. I say, look, food is chemical energy, right? So you eat these things and they have bonds in them. They have, especially hydrocarbons, right? They're incredibly rich in stored potential energy within the carbon-carbon and carbon-hydrogen bonds in particular. These are the most energy-rich bonds. Metabolism is a fancy word for taking the chemical energy that is stored within the bonds, again, primarily between carbon and hydrogen and carbon, and turning that into electrical energy. And that electrical energy is used to turn back into chemical energy. So you take the electrical energy in the electron transport chain, for example, and then you shuttle it back into chemical energy in the form of ATP. So basically, food to ATP is just changing the form of energy, but obviously energy is conserved in this process. And that's just kind of like a hand-waving, high-level explanation. But I think for the purpose of this discussion, we should go a little deeper and explain and we don't have to even get into fatty acid at this point. We'll probably come to it later. But even just through the lens of glucose, which of course we'll treat as synonymous with glycogen. So when a molecule of glucose is being used by a cell, and that cell needs to make ATP, can you walk through in a little bit of detail how it does it and what are the different nodes or paths that it can go down?
Yeah, well, that was a very good explanation. I don't think what I'm about to say is going to advance this understanding much more. So when glucose is activated to break down, and we can also talk about getting glucose into the cell.
Yes.
And there are barriers to that. And
well, actually, go ahead and do that, George, because I know lactate is going to come and figure into insulin. So why don't you do that? Why don't you start at getting glucose into the cell, and then we'll keep going.
Yeah, so glucose is a molecule that can be quite high in the blood, but it can't get into the cell unless it meets a transporter. And some of the transporters are constitutive. They're in all cells. Like the brain has the first transporter discovered was named 1, and then 2 and 3 and 4. And 4 is important because 4 is expressed in most of our body, in our muscles and in our fat cells. So we need to have these glucose transporters at the cell surface. And depending on the various kinds of signaling, insulin is the typical signal. Also, muscle contraction will move these transporters to the cell surface. Now glucose can come in. So when I teach glycolysis to my class, and I use one of the textbook figures where it starts out with glucose, I put the brakes on and say, no, we need to put a membrane barrier in here. We need to get glucose into the cell, and then it can be metabolized. And it's usually once the glucose is in the cell, then there are 2 things that can happen. It can be stored as glycogen, but if there's an energy need, it will enter the glycolytic pathway and be degraded. There are a couple of important regulatory steps which are involved, phosphate level and redox, but I'll just say that the glucose splits into 2. And so we have a 6-carbon molecule that makes 2 3-carbon molecules. And depending on who you are and how you write this pathway, the last step is either pyruvate or it's lactate. And what we found recently, because we traced the glucose to see what it makes, glycolysis basically goes to lactate. So it's a series of steps. One reactant, one product is a reactant for the next step, and there's a splitting of 6-carbon molecule to 2 3-carbon molecules that progress to lactate. And so the process itself is basically pH neutral.
Let's just make sure people understand that. So what you're saying is, if I heard you correctly, George, the glucose comes into the cell. Let's just assume we're not in a storage state. We're in a utilization state. The 6-carbon ring is split into 2 3-carbon halves.
Mm-hmm.
Now, a second ago, you said you have 2 potential fates there, right? You could make pyruvate or you could make lactate. Is that correct? Or did you say that it's all okay? And you said that either choice is pH neutral. Is that correct?
Well, actually, if you get to lactate, it's actually an alkalizing step. But the whole process itself is basically pH neutral. And for our discussion of muscle, so we're embedded in muscle now. That's been our thinking, my career, 50 years in this, and for the whole field, it's all muscle. But we'll get to what happens, when we take carbohydrate as we go through this. Yeah, so we're going to split this molecule, and it's, as you described, it's potential carbon energy. So one way to think about metabolism is the flow of energy, and carbon energy, carbon-derived energy. And at some point we could talk about its integration with fatty acid, maybe amino acid metabolism. But we're really, in a basic biological sense, talking about the energy highway, which is carbon-based, and it's reduced. So chemically, then, when it can be oxidized, a lot of energy is released, and we can capture that as ATP. Now, actually, when we're doing just glycolysis in a muscle, and I need to say that when our muscles are working, about 80% of that carbon flow comes from previously stored carbohydrate glycogen. So that's our carbohydrate energy source. And we have done numerous experiments looking at carbohydrate oxidation in exercise and the use of glucose. And really, the body protects its glucose pool because there are certain cells that really need glucose, like our brain. And if we got our muscles going, they could suck up all the glucose and leave us really hypoglycemic, and we would crash. So actually, just the active muscles are going to take up glucose. But it's not going to be a major part of the energy. It's a significant part, maybe 20, 25%. Most of that carbon is going to come from previously stored glucose, which we call glycogen.
And for the listener who might not be as familiar with that, about 80% of the body's total glycogen or stored glucose is found within the skeletal muscles, while the remaining 20 to 25% would be in the liver. And the way I think about it is that the liver's primary responsibility is regulating blood glucose for the brain, whereas having all of that stored glycogen in the muscle is, as you said, an important source of fueling the muscle so that the muscle doesn't have to, for lack of a better word, steal glucose that from the circulation that would otherwise be imperative to keep the brain happy. But of course, one of the very important things I am sure we will discuss is the role the lactate plays in replenishing the liver, which, if I'm not mistaken, was another Nobel Prize, probably now somewhere in the mid to late 40s, if memory serves correctly, vis-a-vis the Cori cycle.
Yeah, I think 1947 was the year.
Well, let's talk a little bit about that. I mean, I think we're kind of marching our way through history, but that was another big seminal involvement, so let's talk about what happens to lactate when it is produced in the metabolic process of breaking down glucose. And I guess the other question I would have, George, just for the listener, what determines that path choice? Let's not talk about a cancer cell, for example, but let's just talk about a normal muscle cell that needs ATP. It's got its glucose, it splits it in half, it's got its 2 3-carbon units. What are the physiologic pressures that drive towards towards pyruvate versus lactate?
Yeah, so we have a couple of steps that depend on redox, but One of the things that's been noticed by our colleagues who really have done a lot of muscle biopsies is that it's not the ATP level that falls, because the whole system is set up to maintain homeostasis of ATP. But we get changes in what NAD and ADH ratio or redox, but we get changes in ADP, adenosine diphosphate. So when we have this ATP molecule, there are 3 phosphates, and we get energy by splitting one off. And it gives us ADP. Turns out that's a big signal to activate these enzymes of processing glucose. So, and we know that in a lot of ways. If we just take an isolated mitochondria, I take a muscle, isolate the mitochondria, and we want to turn them on and make them start doing something, we add ADP. And away they go, and they start to phosphorylate that ADP and make ATP by the chemiosmotic process, which you described as electrical energy. So yes, the muscle mitochondrial network works like a big battery, and it's a battery. It's just not, I don't know if we'll talk about mitochondrial functionality or about its arrangement. It's a network. It's not, they're not just little capsules, this whole network. I call it the energy highway. Other people have called it the cellular energy power grid. Anyhow, that's where the ATP is going to be generated. And to do that, you need this chemical energy fuel, which is pyruvate or lactate. People have assumed that it's pyruvate that goes into the mitochondria, and that's true, that happens. But most of that chemical energy comes in the form of lactate that goes into the mitochondrial reticulum or network, and that's the fuel to run the apparatus of oxidative phosphorylation and make ATP.
And George, I just have to stop you there, because that is such a, again, people who are listening to this who are physicians or have studied this are going to say, wow, hang on a second, that is the biggest departure from everything we ever learned, right? So yeah. I just want to restate what every single textbook on this subject says to paint the backdrop for why this discussion is so interesting, right? So the textbook, every textbook says the following. When you make pyruvate out of glucose, the pyruvate gets shuttled in to the mitochondria, and there we undergo the Krebs cycle, where we very, very efficiently produce massive amounts of ATP, and the only byproduct is carbon dioxide and water. And so as we are undergoing aerobic respiration, we're consuming oxygen and pyruvate, generating, again, incredibly efficient amounts of high-volume ATP, and out comes carbon dioxide and water, which is what we're breathing out. Conversely, when you take that glucose and you make lactate, you do generate ATP, but very, very little amounts. And that lactate now needs to escape the cell, make its way into the circulation, where it can go back to the liver and be turned back into glucose via the Cori cycle to begin again. But unless I missed, I don't know, like a couple months of my education in medical school, I do not remember any discussion of lactate going into the mitochondria directly from the cytoplasm as a substrate for ATP production under aerobic respiration. So it's possible I just missed that, but is it more likely the case that most people would believe what I just said?
We've been teaching glycolysis wrong for 100 years. And probably you learned that in junior high school or high school. And physicians and scientists are smart people. And if you hear it at the high school level, and you hear it in college, and you hear it in medical school, well, that's what you think it is. And that's an assumption that's really deleterious. So that lactate, that's formed, enters the mitochondria, and we have shown that there's a mitochondrial carrier for the lactate to get in, and we've shown this, and we call it the mitochondrial lactate oxidation complex, and we have electron micrographs, we have light micrographs to show how this process works, and the enzymes are there for lactate oxidation. But lactate is important as a fuel, And as you describe, really the first articulation of a lactate shuttle was by the Coreys. And they showed that a dog muscle made to contract with adrenaline or otherwise will release pyruvate and lactate, which will recirculate to the liver and become glucose. So that's a way to supply blood glucose during exercise. So the muscles are actually not only fueling themselves, they're fueling adjacent tissues, and they're fueling the brain by this lactate shuttle or Corey cycle.
Is that a rate dependent, or rate's the wrong word? Is it a velocity or a demand dependent process? In other words, if ATP is being demanded at a very high rate, is the body that in that scenario preferentially taking the lactate back to the Corey cycle, back to the liver to make glucose, versus if the body has the quote unquote the time, it can make the long-term investment in getting more ATP per unit carbon by putting lactate into the mitochondria? Because again, the traditional thinking on this is we go down the lactate pathway when we are demanding ATP faster than oxygen can be supplied to the mitochondria, and that's why it's referred to as this anaerobic pathway. And if we have the time, if the ATP demand is low enough that we can afford to get oxygen to the mitochondria, well, then we would always preferentially go down the oxidative phosphorylation pathway. So in the discovery that you were talking about, which again, I can't overstate how sort of mind-boggling that is. What determines the path?
Well, it's this ADP to ATP ratio. That's what accelerates glycolysis.
So if the ADP to ATP ratio is low, which tells us ATP is being consumed quickly, does that drive lactate into the mitochondria or out to the liver?
Yeah, so recently, actually, not us, but others have shown that lactate activates the mitochondria. We have shown that lactate is a preferred fuel.
So tell me what that means. What do you mean by lactate activates the mitochondria?
It activates lactate dehydrogenase, the enzyme in mitochondria, which allows the carbon flow to go into the mitochondria for oxidation.
Does that mean that it also amplifies other substrates flow through? So in other words, if you have a bunch of acetyl-CoA hanging around from fatty acid breakdown, is that also being stimulated to run through the mitochondria at an accelerated rate?
Good point. To the contrary. So lactate is not only, if we have compared glucose to lactate to fatty acids. So lactate is preferred over glucose in the brain and muscle, wherever. But when you the path of degradation of lactate is to generate this acetyl-CoA. And that inhibits the enzymes that transport acetyl-CoA or fatty acids into the mitochondria. So lactate basically shuts the door, blocks fatty acid metabolism. So it inhibits, and Ineos and I have shown this, blocks the CPT1 and 2. The carnitine palmitate transporters. These are transporters that allow fatty acids to get into the mitochondria for oxidation. So, yes, there is a competition amongst substrates, and lactate shuts the door for fatty acid metabolism.
I'm struggling to understand teleologically why that makes sense, which just tells me I'm missing something, because I would never for a second suggest my intuition should be better than a billion years of evolution. But why is it that we would ever want to shut down a substrate for which we have an infinite supply, right? Because we're carrying around more than 100,000 kilocalories of fatty acid. Why wouldn't we always want to maximize our ability to utilize that substrate at the expense of something relatively finite as glycogen, which of course is necessary to even make the lactate?
Well, that's part of the fight and flight mechanism. So in terms of our survival, what are we going to save the fat's for? The tiger?
Okay, I understand. Good point. Thanks for catching that. Thanks for correcting my stupidity. No. So you're saying the reason, Peter, is if you are in a lactate dependent state, there's something has gone wrong. You're basically in a sympathetic state, and you don't have the luxury of slow burning fat.
Exactly.
Yeah. Okay.
So fats are really important. You can see this play out in the natural world. So we fight, we hunt, we escape, and this is really glycogen, glucose dependent. Now our energy stores are depleted. That's in recovery is when we're going to use these fats.
Well, this is very interesting, and now it actually makes more sense with something we're going to talk about later, but I'll plant the seed right now. We discussed this previously with Inigo, but I know we're going to talk about it again. You look at lactate levels in individuals at rest who have type 2 diabetes versus lactate levels at rest in world-class athletes. There's a significant difference. And the great irony of that is the very low levels of resting lactate in the athlete mean that at rest, they're quite capable of oxidizing fatty acids when sympathetic drive is low and demand is low. And yet, paradoxically, the individual with type 2 diabetes who would most benefit from fatty acid oxidation is presumably now inhibited in doing so because of those elevated levels of lactate. Is that probably a fair assessment?
Yeah, that basically shuts down the fat metabolism. But think about this. This is my old thinking. That lactate there is elevated because of lack of disposal, not necessarily production. It's there because of failure to dispose. So what my new thinking is, the body in a diabetic situation has a hard time taking up glucose because of those insulin signaling, and the GLUT4 mechanism is not working very well. So think about lactate not as a stress, but as a strain. So now we're going to bypass this inhibition of glucose uptake. We're going to provide actually the preferred carbohydrate. So, and we see that not only in diabetes, we see that in the heart after MI. Lactate is a preferred fuel. Well, you think that we had an MI because we had ischemia and we had a blockage. Why would the heart prefer fast-acting fuel versus a slow-acting fuel? Because it needs energy, because it needs to survive.
How does one measure the kinetics by which 1 mole of lactate versus 1 mole of glucose versus 1 mole of fatty acid can produce ATP? What are the tools that allow you to make the observation that one fuel is preferred over the others, or that the kinetics of one fuel are faster than that of another?
Yeah, thank you for that question. We use isotope tracers to do that. So when our first experiments to give with rats to give carbon-14 labeled lactate, then we would go into the tissues and try to measure it. It's all gone. It's been burned. It's out into the atmosphere.
Meaning the only place that C14 carbon would be found now is in carbon dioxide if you had a calorimeter.
Yeah. So we have done a number of experiments in collaboration with others or just in our own. We've developed a technique called the lactate clamp technique. And it's analogous to the glucose clamp technique, which some of your physician listeners will know about. That's where you raise the glucose level to a certain level, and then you can study the production versus the disposal. So we infuse lactate up to 4 millimolar, and others have raised lactate even to higher. When we do that, we can measure the arterial venous difference for glucose uptake, and it's suppressed. In a study with UCLA, we did some PET scanning, and this is a fancy way to say we can take a picture where glucose is being metabolized in the brain. So this is done with a traumatic brain injury patient, and you could see there's a blockage for glucose to get into the left frontal lobe in this patient. The next day, we infused lactate to 4 millimolar. It completely stopped the glucose uptake. No glucose uptake in a PET scan. I can show you the image.
And so I guess my question is this, George. So that clearly demonstrates that lactate is preferred over glucose. But I think the jugular question is the brain getting more ATP from the lactate as a preferred fuel than the glucose, which has one area of hypoperfusion? In other words, are you able to, by providing the preferred fuel, actually get more energy to the neurons that are injured?
Yeah, so not a colleague, but a colleague in science, Pierre Magistretti, in Switzerland, has developed what he calls the astrocyte neuron lactate shuttle. And that's really sparked a lot of interest in the metabolism of astrocytes. So for years, I taught, maybe you did, and you believed that glucose was the exclusive fuel for the brain.
We know at a minimum that beta-hydroxybutyrate would also be another fuel for the brain.
It could be, but not if glucose is around or
Correct.
lactate's around.
Yep.
So the lactate will come in through the, so in the injured brain, there's for some reason, maybe there's a block at the splitting enzyme in the glycolytic pathway where the injured brain needs glucose, but it only takes up maybe 50% of what's typical.
Mm-hmm.
So the brain is in a metabolic crisis after an injury. Globally, it is. So there's some neural networking where it just stops glycolysis. So traditionally what physicians would do is give glucose, infuse glucose. And the glucose uptake, the metabolism is blocked, so the glucose doesn't get in and doesn't do anything. Or give insulin plus glucose.
Yes, intranasal insulin was one of the tricks there, right, to try to drive more glucose uptake.
Yeah, but the brain doesn't express GLUT4. So that's not going to do much. But now we have, instead of the 6-carbon molecule, we have a couple of 3-carbon molecules, and the lactate transporters are highly expressed in the brain. And we know that under normal circumstances, what's happening is that the glucose is coming in, being taken up by the astrocytes, made into lactate, which are bathing the neurons in lactate, and lactate is the fuel for neurons.
I misspoke a second ago, though, George. I could have sworn George Cahill demonstrated in those very famous fasting studies, circa 1960s, 1970s, that even in the presence of glucose, the brain was still taking up significant beta-hydroxybutyrate. So if I'm not misremembering this, these subjects were fasted for a very long period of time. I mean, these were 40-day water-only fasts. So these individuals had beta-hydroxybutyrate levels of 4 to 5 millimole, which actually exceeded glucose concentration. By this point, glucose concentration would have been about 3 millimole in steady state. So for folks listening to us who don't think in European terms, 3 millimole of glucose means these people were walking around with a blood glucose of 55 milligrams per deciliter. But it really never went below that. So that's obviously pretty hypoglycemic, but it's, that's still 60% of what you would walk around with normally. And glucose was meeting about 50% of their brain's demand, and about the other 50% was coming from the BHB. So at least in that situation, the brain would split fuels. Now, of course, I don't know that Cahill was measuring it, so we just don't know what lactate was doing there. But it's an interesting observation that the brain would split its fuels in the presence of BHB and glucose.
So I'm going to agree with you to the extent that there's competition amongst substrates.
Yeah.
More glucose, less fatty acids. More fatty acids, vice versa. Okay, ketones come in by the lactate transporter. So the monocarboxylate transporter allows ketones to get in.
Meaning BHB enters the cell through the same MCT transporter that would bring lactate into the cell.
Yes.
Okay.
And,
yep. I think I used to know that.
we did this early on, and there's a greater preference for lactate over beta-hydroxybutyrate. So if the concentrations were the same, the transporters would move lactate as opposed to beta-hydroxybutyrate.
In other words, if we could do a thought experiment, or actually a literal experiment, where you could infuse, so let's say you could clamp everything. So you could have a person walk around with 4 millimole of glucose, 4 millimole of beta-hydroxybutyrate, 4 millimole of lactate, and you're peripherally clamping those concentrations. So you have equal concentrations of 3 fuels that the brain could use. Mm-hmm. What is your prediction for neuronal uptake based on that scenario?
If it's an uninjured person.
Yes, let's start with that.
Yes, the preference would be for glucose and lactate.
And would it be roughly equal amounts of those two in an uninjured brain?
Roughly, probably.
Okay.
So, we've published on it. We worked with the UCLA neurosurgery. We did these experiments with dideuteroglucose and 13C lactate. So probably about the same. Yeah.
Okay. And then now let's talk about the injured brain. So now you have a TBI patient and you're doing the exact same thing. You're infusing equal concentrations of glucose, lactate, and BHB. What would you think? Everybody knows clinically that glucose is going to be suppressed. How much of that is made up for by the lactate versus the BHB?
Yeah, so if lactate's around, it's going to suppress the BHB.
So lactate could be the dominant fuel in the injured brain.
Yep.
So the implication of this, at the risk of stating the obvious, is we should be giving brain-injured people intravenous lactate round the clock to heal their brains.
I think so.
How many people are aware of that, agree with that? I mean,
So we, for various reasons, we lost our collaboration with UCLA neurosurgery, but they were in the stage 2 clinical trial of infusing lactate. And they weren't the only ones. There's a group in Switzerland who preferentially gives hypertonic lactate to TBI patients, and they appear to do better. But we were hoping to have a clinical trial, multi-center trial, demonstrating, the use of lactate as an augmentation to glucose in the TBI state. But I don't know what the status of those studies are, but there was a stage 2 clinical trial that has started at UCLA.
George, has anybody labeled lactate with FDG so that, or some like the equivalent of an FDG, so that you could do a PET scan and actually demonstrate significant uptake of lactate in a brain, and then actually do that experiment in an injured brain? So, because what I'm imagining is everybody has seen the images of the injured brain under standard FDG PET, where you have the hypoperfusion in the area. And by the way, this is relevant in diseases like Alzheimer's disease. This is relevant in dementia, where we see hypoperfusion of glucose. But it would be interesting, if it hasn't already been done, to see what the uptake of lactate is if you can put an F18 onto lactate, which I assume is a trivial task, right?
I don't know about that, but our colleague here at Berkeley, Tom Buttinger, really helped develop PET and helped make NMR clinically relevant. He did experiments with carbon 11 lactate. So in the PET scanner, it gives a signal, as does fluorodeoxyglucose. So that way, you could see lactate taken up by the brain. The difficulty with those experiments, I think the half-life of carbon 11 is on the order of minutes, 20 minutes. So the first experiments involved somebody in a cyclotron making carbon 11 lactate, putting it in a lead-lined station wagon, driving it down, running it through a column to remove the strontium-82, and then infusing it into a brain and imaging the brain. So it's possible with carbon-11 to do that experiment.
But any reason not to just put F18 onto lactate? Is that chemically not feasible?
I haven't thought about that.
It seems like that would be a very interesting experiment, though, right? I mean, or at a minimum, just to generate a hypothesis, right, that says we can fill an energetic gap by using lactate and simply observing a difference in perfusion pre and post lactate infusion.
I'm making a note.
Okay, yeah, it's possible. If it hasn't been done, I'm sure I'm missing something obvious about the chemistry of it.
Budinger would do it when he would do the experiments with glucose or lactate. He also would give rubidium-82, which is a marker of flow. So you would want to do exactly what you described. You would want to know the uptake relative to the flow. So if the flow is depressed in an area, then you would expect the uptake to be less. And so in the Budinger method, you need to do 2 isotopes simultaneously, and that's really tricky and hard to do clinically. It's really, as you described, could be a great experiment, but getting it to work in clinical centers would be a real trick, real investment.
Yeah. What about just in sort of rodent studies of hypoperfusion? I assume that would be an easier place to look at, a TBI model where you ask if lactate can rescue the animal.
Well, we could just do that even without a tracer, right?
Exactly. That's my point. Yeah, you could get around the whole tracer component by just doing that. Is there any issue with infusing lactates at higher concentrations? Is 4 millimole sufficient, or is there any reason you couldn't put in 6 or 8 millimole?
Yeah, I think our friends in Switzerland have got it up to 8 millimole. But then, you're using hypertonic lactate. So what you can give vascularly, people need to understand it can't be too concentrated to make the blood really affected poorly.
When we give patients like an intravenous bag of lactated ringers, what's the concentration of lactate in that?
It's really pretty
solution?
low.
Yeah, okay.
Yeah. So what they do is they do half molar sodium lactate. And we need to understand when we have half molar sodium, it's half molar sodium and half molar lactate. So the osmolality is twice that. It's 1,000. So that's sort of the upper limit of what you can give safely intravascularly without causing phlebitis or without causing crenation of the red blood cells shrinking and getting all distorted.
Yep, makes sense. But 4, you can clamp a person at 4 millimole quite safely and easily.
Yeah, and I think, the idea was to do that for a couple hours a day, not continuously. Again, because we'd have to make sure that the kidneys were not affected because we're giving a lot of sodium. That was a concern.
So I was going to ask you about that. So what's the manner in which the lactate is delivered? In other words, what else has to be delivered with it to balance the solution?
So a lactate anion has a negative charge. So to put it into the blood, you need to have something with a positive charge. And so the major cation in our blood is sodium. So what's used is sodium lactate. So in our studies, we could clamp to 4 millimolar and hardly raise the sodium level in the blood. So we thought that would be an approach that would be reasonable to work with a patient. But again, you are going to be giving sodium, so you have to make sure that in the patient they have good kidney function. Now I see you're making notes. That's good.
Oh, you have no idea how many notes I make here, George. The highest lactate I've ever measured in myself is about 18 millimole. Obviously after a very intense bout of exercise. Not surprisingly, anybody who's measured lactate in themselves, anything over 10 is a very, very uncomfortable situation to be in. Let's go back and talk about what's going on and where my discomfort comes from, because it's not the lactate that's causing me discomfort, correct?
No. Lactate is there to moderate. It's a strain response. It's helping to protect you. But you probably have a severe acidosis.
I'm feeling like I'm about to die because my pH is probably 7.05 or something like that.
Yeah, yeah. And can I ask you a question? Are you ever hungry after one of these episodes?
Not at all. In fact, it's usually you're about to vomit if you don't actually vomit.
Yeah. So actually, lactate crosses the blood-brain barrier and works in the brain, and the dentate, not in the dentate gyrus, in the hypothalamus, to inhibit your appetite. So those of us, who run 440 yards or 400 meters, we're not hungry for 3 hours, right until that lactate level is cleared, which is really a good reason. People have written about this recently. It inhibits appetite. Lactate suppresses ghrelin. It works directly into CNS. So an advantage of doing an exercise, not like that one you did, Peter, but getting lactate up to maybe 3 or 4 millimolar would actually help satiate people. I know there are people who say, well, I exercise and I'm really so hungry afterwards. Well, you're not exercising hard enough. But if you do raise lactate, it will cross the blood-brain barrier. It will inhibit ghrelin secretion, and it will suppress the appetite.
That's a very interesting point. And I know that people who are listening to this who are familiar with lactate testing, which I know is a bit esoteric, but there is a fundamental difference between having your lactate at 1.5 millimole or 1 millimole, which is where it might be if you go for kind of a brisk walk, versus being at 4 millimole, which is, not a level you can sustain indefinitely, but it's not, it's also not so strenuous that you could only do it for a few minutes. I mean, that's sort of, a fit person could hold that level of exertion for 30 to 40 minutes.
I think your listeners will know that 4 millimolar is talked about a lot.
Let's talk a little bit about differences between athletes and non-athletes, which again, I think it becomes very illustrative because they're simply different metabolically, right? So that it's not just that the athletes are stronger and the non-athletes are not. But what's happening in terms of fuel partitioning that differentiates a highly, highly trained aerobic athlete like a cyclist with, someone who's got insulin resistance? What are the differences in their ability to utilize fuels?
Great. So let's back up just a little bit and go back to the mitochondria. Mitochondria are the sinks or the disposal units. So when anything fluxes, as you described in the body, like carbon flux, it has to go from a production or entry site and has to go to a removal site. And the mitochondrial network is the removal site. Now, when a highly trained athlete exercises, and here we need to talk about relative or absolute power output. So let's say 65% of VO2 max or 65% of effort. For an untrained person, well, that's not very much exercise, really. They'll get to 65% of VO2 max at a very low power output. Now we take the trained athlete, put him or her at their 65%. They're generating a lot of lactate, but they're burning it. And as you described earlier, it's recirculating to the Cori cycle to support blood glucose. So even if you just measure the concentration, you don't have the whole story. You don't have the flow, you don't have the flux rate, you don't have the partitioning sensation. Now, if you take that same athlete now and you push him to a lactate that elicits maybe 6 or 8 millimolar, they're going to be really a lot of differences there. And now you've exceeded their capacity of the mitochondria to clear lactate. And also, you're probably going to have shunting away from the gut. This goes back to something we mentioned in passing. So gluconeogenesis, the making of glucose from lactate, depends on good liver blood flow. When you start going really, really hard, your blood's going to go to your muscles, basically, and you're going to clamp down. You're not going to perfuse the liver. So now the gluconeogenesis goes down. regardless of who you are, when you sort of take the liver and the kidneys out of circulation. Now, and of course, those are major organs of lactate disposal as well. I said 25% earlier. If you eliminate those by basically clamping them off, then the lactate level is going to be higher.
I want to go back to something I asked you earlier, but I want to make sure I captured what you said. As the individual is increasing the energy demand, they're making more and more lactate. Is ADP or ADP to ATP helping to determine when the lactate is going in the mitochondria versus back to the liver? Because in the scenario you described, where energy demand is going up and up and up, and therefore perfusion is going down in the organs that are able to recirculate lactate, you would think that the body would just say, okay, no problem. I'm going to shovel more lactate into the mitochondria. I've got a perfect engine here to generate more ATP. In other words, why is that a problem, that the lactate now can't be cleared as efficiently through the gluconeogenic pathways?
Yeah, so go again to your example of the athlete. When we train, we increase our mitochondrial mass, maybe 100%. If we train, we'll raise our VO2 max, maybe 10, 15%. So there's more plasticity in the muscle to increase the mitochondrial mass. And I think really that's the key to Inio's success with his athletes. He trains them so they increase their mitochondrial mass.
Wait, how much did you say you increase mitochondrial mass by?
Well, you can double it.
Over what period of time?
Well, for the first study on this appeared in 1967. The Journal of Biological Chemistry was in rats. It was by John Halazzi. And you could, over the period of several weeks of training rats, you could do that. After that, we extended those studies a bit with Kelvin Davies when he was here. And we were, again, sort of doubling of the mitochondrial mass. Others have looked into the muscles of athletes and found that they have more than twice the mitochondrial mass of the average person. And that, of course, is a lot selection.
Sorry, just to be clear, this is mitochondrial density. So for 1 gram of vastus lateralis in an athlete versus 1 gram of vastus lateralis in a non-athlete, you'll see 2x the mitochondria?
You'll see 2x the mitochondrial mass. So I don't talk about...
Yeah, not necessarily the number of mitochondria, because the volume, And how is that conveyed? Is that larger mitochondria plus more mitochondria that amounts to that doubling?
We talk about the mitochondrial reticulum. So think about a tree budding and branching out, leaves.
Yep.
So if you do a thin section, you'll see, and you do point counting, 1 mitochondrion, 2 mitochondrion, 3 mitochondrion, 1,000 mitochondrion, but they're all part of a network. So what you have is a bigger energy delivery system that goes from the cell surface deep within the fiber to this network. Yeah. And again, some people call it the cellular energy power grid.
And to your point, which is, has the experiment been done to demonstrate the causality of exercise there? In other words, do we have the experiment where you take untrained individuals, do the muscle biopsy, compute mitochondrial density, mass of mitochondria per unit mass of muscle, train them for 4 to 6 months, repeat the biopsy, and see if the training is leading to the doubling, rather than just saying, well, athletes are athletes because they have more mitochondria?
Yeah, well, it works both ways. If you're born with that and you go into athletics, you're successsill. And then,
that's right, yeah.
And then if you're not, then you become a professor.
That's sort of something I'm curious about.
It goes up proportionally. And interesting, all the enzymes that are, as far as we can tell, all the constituents that make up this mitochondrial network go up proportionally. So you get twice as much Krebs cycle enzymes, twice as much electron transport cycle enzyme. You basically activate the whole the whole system.
So, George, I was taught the following, which I'm now almost assuming is going to be at best an oversimplification, and at worst, I might just be abjectly wrong. You mentioned something called MCTs a moment ago. Do you want to tell folks what an MCT is?
Oh, yeah. I had to explain this to my wife, Rosemary, the sports medicine doctor. What's an MCT? Well, we were looking for the lactate transporter protein, and we got scooped. Somebody found it, and she called it, and it was Dr. Christine Kim Garcia in the Goldstein lab in Dallas, and it's a Nobel Prize lab. And she found they were looking for transporters of things that contributed to cholesterol metabolism. And she found this protein, and she didn't know what it was. And she found out it was a lactate transporter. And so they were called monocarboxylate transporters. And now it's like the glucose transporter field, where we have the first isoform and the second one and the third and the fourth. There are actually more than 4 now that have been discovered.
When was the first one?
About 2000.
Okay. So what I was taught, again, we'll see how far off base I am, was that one of the benefits of training was increasing the density of MCTs. So in other words, the harder I trained, the more I increased the density of these MCTs in my muscle cells. And what that allowed me to do was produce more lactate, but get it out of the cell and back to the liver. So, you imagine a little cartoon where I've got a muscle cell, I'm untrained, and I've got 50 MCTs. And after training, I've now got 100 MCTs after a period of time, not acutely, but, years of training or whatever. And therefore, I can now make twice as much lactate and get that lactate out. Now, of course, all of this was predicated on the model that said more lactate in the muscle is bad, because with lactate goes hydrogen, and hydrogen inhibits performance. So again, that was all viewed through that lens. But was there any truth to the idea that as we train more, we increase the density of MCTs, which, if nothing else, I assume would give us more flexibility in this lactate flux game?
Yes, we've done this in animals, and we've done it in looking at trained and untrained people. And we can see an increase in the abundance of the MCTs. Now, that helps 2 ways, because getting lactate into the mitochondrial network requires an MCT. So we were bold enough to look at the mitochondria and find MCTs. So people think, well, it's just on the cell membrane and it's good for export. And that's true. But in oxidative muscle fibers, with the abundance of transporters, many of them are in the mitochondria. So the lactate will move into the mitochondria as well as can be exported. So then we see a difference between fiber type. Fast glycolytic fibers will be pale in color, and they're pale because of less heme oxygen compounds. They'll have less blood flow, fewer capillaries per fiber. They'll have less myoglobin, and mitochondria are the color of liver, or vice versa. Liver is the color of mitochondria. So those fibers, when they're made to contract, they have a lesser mitochondrial density. They will export lactate. But they can export it to a neighboring red fiber. So we call this the cell-cell lactate shuttle, where a fast glycolytic fiber produces lactate, and it's consumed by an adjacent fiber and never even appears in the venous blood except as CO2.
I'd never heard that, George. So just to make sure the listeners are following and that I'm following, we've had many podcasts where, of course, we discuss type 1 and type 2 muscle fibers, colloquially referred to as fast twitch and slow twitch fibers. So the slow twitch fiber, the type 1 fiber, is the red fiber. It's the fiber that is dense in mitochondria. It is the one that has the capacity for oxidative phosphorylation. It is less powerful, but much slower to fatigue, right? Then you have these type 2 fibers, and I'm oversimplifying a little bit because there are subtypes of them, I understand, but the type 2 fiber, it's a more contractile, it's a more powerful fiber, twitches a little faster, but it's very fast to fatigue. It's the white fiber because it is lacking in the mitochondria. Does it outright lack mitochondria? And basically it's just a pure glycolytic fiber, correct?
No, there are mitochondria in there.
There are, just a much lower density.
Lower density, yeah.
Yeah. So what you just said a second ago was, as those cells accumulate lactate, they realize that their neighboring type 1 cells can make even more use of the lactate, given that they have a greater density of mitochondria. So they'll shuttle the lactate from the 2s to the 1s. Is that correct?
Yeah.
Wow.
Yeah, so that's actually part of the discovery of the lactate shuttle. So early on, when we started doing the studies on rats and using C14 lactate and tritiated glucose and comparing the flux rates of the two and looking at the various fates of where the carbon goes, we knew that there was in exercise was a large flux, but from the tracer itself, you can't tell where. So a colleague of mine at UC Irvine, Ken Baldwin, did his studies on rats. And he made them exercise hard. Then he measured the lactate levels in blood, in red muscle, and in white muscle. So a rat made to run hard has a very high level of lactate in the fast glycolytic type 2 fibers.
Can you give me the approximate concentrations in that type of an experiment between blood type 1 and type 2?
Yeah, so, but I'll give you this, just to finish the analogy. We can put some numbers on it. So then he measured the lactate level in the arterial blood. And of course, it was lower. And the red muscles, the lactate level was lower than in arterial blood. And that gave rise to the idea that the fast fibers were sharing lactate, not just to the venous blood, but to the red fibers that were adjacent. So the numbers, I'm trying to remember, this is back 30 years, what the numbers were. It would be something like in the fast fibers, it would be something like 10 to 12 milliequivalents. In the blood, it would be 4, and in the red fibers, it would be 3.
And then in the arterial, but the 4 was in venous blood, correct?
In blood? No, that would be arterial.
That was in arterial blood. Got it.
So that gave rise to this idea of the shunt, or a shuttle. Some people call it a shunt. From white fibers to red fibers. And as you described, it's easy for the white fiber to export the lactate, but it will export it in a 3-dimensional sense, being surrounded by slow red fibers who can oxidize lactate.
God, this is just so. When did you first find MCTs on mitochondrial membranes? What year did you first publish that?
About 95.
So what percentage of the relevant scientific community acknowledges that now? Again, am I just taking this, is it taken for granted within your world that is completely settled? And is it just that that hasn't made it out to any of the textbooks yet?
Oh, well, Tom Fay and I are revising our textbook. We're going to get it right. But yes, there's been a stonewall silence. For instance, in Science magazine, they published papers on the mitochondrial pyruvate transporter, 2 papers simultaneously about this discovery of the pyruvate transporters. Previously, we had shown the mitochondrial lactate transporter. It wasn't even cited. Neither the editors or the reviewers knew about it. So now things are changing, Peter. So actually right now, there is a lot of interest in lactate.
So this is interesting. Why? I mean, I know this is kind of these are difficult questions to answer, so I'm sensitive to that. But why do you think that something that was discovered 30 years ago that appears quite germane to the physiology of everything, but if nothing else, just through the physiology of exercise, but it clearly extends beyond that. Why do you think that this isn't more widely understood, even in the physiologic circles that you travel in?
Yeah. I think I said it earlier. People who do science and medicine are smart people if they learned it a certain way, and that's their set point.
But I tend to differ between scientists and physicians, and I say this as no disrespect to my profession, but I think that makes more sense at the physician level where, look, medical school is drinking from a fire hose. It's almost beat out of you to question things because you frankly don't have the time, right? You've got 2 years to learn so much. But I would have to think that that's quite different for people who choose a scientific pathway where discovery, questioning orthodox beliefs, that is the name of the game. Is there something I'm missing here?
So maybe there is a difference between science and medicine in this regard. So when I'm given the opportunity, I will talk to, for instance, the Washington Thoracic Society and go to a meeting and talk to the docs. Because when they see lactate, they start infusing bicarbonate.
Right.
And or they give oxygen. So in the medical field, there's a character, maybe someday you would really enjoy meeting this. His name is Ronaldo Bellamo. He's a world-renowned physician, emergency room physician, and he's written about the fact that pulmonologists need to be more like exercise physiologists with regard to understanding lactate metabolism. He challenges his colleagues to do that, and Bellamo was a big name in the field. So there's been a lot of inertia in this, but I think we're getting some momentum.
So I want to use an example, a real life example, to have you explain the difference in metabolism between two people, me and one of my friends. So this is I'm not going to name him, but I already talked with him about maybe potentially telling his story. So there's a friend of mine who is really an exceptional cyclist. Okay, he is probably in the top. He would easily be in the top 10 amateur cyclists in the country. Okay, so again, for people who you would understand these numbers, but I should just throw out some numbers so people understand what we're talking about. So this is a guy who's in his late 40s, and he can still put out 5.3 watts per kilogram for an hour. So that's what we would call his functional threshold power. So when he is on a bike, he can put out 420 to 430 watts for 60 minutes. And whatever, he weighs about 80 kilos. So again, I understand that people listening to us might not understand what 430 watts feels like, let alone what it would feel like for an hour. But I know you understand this, and I think there are enough people listening to us that understand this, that we can still justify the time on this topic. So I just want to explain to you, here he is, this incredible cyclist, and actually a great triathlete as well. So great swimmer and runner. But really on the bike is where he shines. And these are numbers that at his age are almost unheard of, and frankly would still be at the levels of a low-level professional cyclist. Okay. Contrast that with me. I'm a very mediocre cyclist. Even at my best, my FTP was lower than his, right? At my very best. Mm-hmm. And today, I don't know, my FTP, if I'm lucky, might be 3 to 3.5 watts per kilo. Very low. Okay. He was over at my house last week, George, and we were lifting weights together. Now, he doesn't lift weights anymore. All of his energy goes into cycling, and I do everything. I'm kind of a jack of all trade, master of nothing. And so he was lifting weights with me. We were doing some leg exercises, and 80 kilos is pretty big for a cyclist. So he doesn't look like a tiny little cyclist, especially in the legs. And so I put him on a machine where I was doing some squats, right? And I just assumed he would start at a weight very close to what I was doing, a little bit less. I maybe had him at 20% less weight than me. And I said, tell me how this feels. And he said, oh, there's no way in hell I could move this. We ended up having to take it down to half the weight that I move for him to be able to do the exercises. And I was really thinking to myself, this is a very interesting lesson in physiology, right? Because his legs are so superior to mine in generating absurdly high wattage for a long period of time. Yet when I'm, asking him to do this different type of task, which is clearly more recruiting of a type 2 muscle fiber, he doesn't have the contractile force. So he and I ended up having a great discussion about this because it was like, oh, it's so interesting that, you're not as strong in this regard as I would have expected, and yet you're so superior in this other way. And what we got talking about was the differences in our metabolism, right? Which is clearly he is able to do something. Because again, what's more interesting to me is not that he's not as strong as me on a squat. It's how much stronger he is than me on a bike, right? So that's a long-winded background, but now I want you to imagine you had muscle biopsies of both of us, right? So now you've got his quads and my quads. What is it about him that is allowing him to hold 430 watts per kilo, 430 watts for an hour? What is happening at the level of fuel utilization that allows him to be so different from the rest of us, regardless of how strong we are? And that's really the point I'm trying to make, right? What is it that he is doing that is so special and that which all, exceptional athletes can do?
Well, not all. It's sport specific. So
yeah, all exceptional cyclists, right?
Yeah,
or endurance athletes.
You described it earlier as the flow of energy. And so I would guess that he was mostly type 1 fibers. These red fibers that are highly perfused, that have the mitochondrial reticulum really highly expressed. So he can have a high carbon flux and sustain it. He can generate large amounts of lactate and clear it. And some of the lactate probably goes into his blood and helps maintain his blood sugar level. So the fact that he can exert as great a force as you probably means that he's got the slow red fiber type. And he also hasn't learned how to do it. You probably could work with him a couple of times. He might improve, just jump up a little bit by learning.
Well, yeah, by the way, I want to make that point. I am totally confident that in 3 weeks, he would be squatting as, he would be doing as, the same amount of weight than me. Again, the point is not so much that I don't want to suggest that he wouldn't be as strong. It's more that if you gave me the rest of my life, I would not be able to get to 5 watts per kilo.
Yeah.
That's the bigger point, even though ostensibly I'm stronger.
Yeah, because it's different. We're talking about different metabolic systems, or a metabolic system surplus versus a contractile entity that coexist together in the same muscle. And of course, one feeds the other. So in his case of cycling, his muscle power output is limited by the carbon flow that he can sustain.
Okay. So thank you. That's exactly where I want to go with this. How much is he limited by carbon flux input versus metabolic byproduct output? In other words, why isn't he at 6 watts per kilo, which would make him among the best cyclists on planet Earth?
Yeah, I think it's a matter of degree. I think if we looked at a really top cyclist, we would find that they could clear lactate more efficiently than he could. And a lot of that would have to do with the fiber type and the mitochondrial mass that they had.
I see. So in the final analysis, you think that what differentiates the absolute best performers on planet Earth is going to be lactate clearance?
Yeah, it's going to, or we're talking about carbon flux, because that glycolytic flux goes to lactate. And nobody knew that until we traced it. And that gets oxidized. So what you have is this production versus disposal capacity, and he's got a great disposal capacity for carbohydrate.
So when he is on that bike for 60 minutes at 430 watts, if you had to guess, if you could sample his arterial blood, his venous blood, his type 1 and his type 2 fibers for lactate concentration, what would be your prediction?
So we haven't done this with trained athletes, but we've done it with some people who are physically fit and recreationally competent. So you can see lactate very high in the venous effluent of a working muscle. I'm going to just make up some numbers here, 10 to 12. And at the same time, since we had arterial sampling versus femoral venous sampling, when the blood goes around the body, not even one complete passage, it's down to 4 millimolar. So there are lactate pyruvate conversions happening in the blood, in part by the red blood cells and in part by the lung parenchyma, because all the blood goes through the lungs.
Yeah, I was about to say, when you sample that venous blood at 10 to 12 millimole, would it matter if you're doing that pre or post portal vein? Because I would think that if you, I mean, you could not do that easily, but just, you know, if you were sampling it above the liver, wouldn't it be significantly lower, given that the liver is also going to be a huge sink for lactate?
That's a good point. It wasn't a mixed venous sample, but we had a femoral sample. So in part dilution.
So you're doing it pre-liver, obviously. So you're getting the absolute peak level of lactate. That's very interesting, George. I never thought of this. All those times I'm sitting there poking my finger in my earlobe, I'm probably underestimating the venous concentration of lactate because it's already had a hepatic pass, right?
It hasn't had a hepatic pass. It's had a hepatic dilution, and it's gone through the lungs.
So that's potentially a double reduction in lactate.
Yeah.
Well, that's interesting. So you're saying if you're measuring 16 millimole in your finger or earlobe, and assuming you're generating this on a bike, and someone had a femoral transducer in you, you could be more than 20 millimole in the femoral blood supply as it's exiting the muscle, correct?
It hasn't been explored much. We just have a couple of papers on it. One is by both are by Matthew Johnson, and another by Greg Henderson. Matt is, you know Matt Johnson, there's two actually.
I don't.
Okay. So Matt works at Dexcom. He's a research scientist at Dexcom. They make the glucose analyzers.
Yep. Maybe I have crossed paths with him. I know some people at Dexcom, and but oh, actually no. I take that back.
Matt.
I do know Matt Johnson. That's exactly right.
He
did a postdoc in your lab.
He was a graduate student.
He was a graduate student. Yep.
Yeah,
yep,
and he was a postdoc
exactly.
with Sri Nair at the Mayo Clinic. So he's really highly trained. So his dissertation was just to infuse femoral venous lactate and look on the arterial side, and you can see there's a huge change in concentration. And we attributed that to the pulmonary function. But you're pointing out we probably missed the hepatic dilution effect.
Yeah, and wouldn't there be a way to, I mean, wouldn't you just be able to use like C14 lactate infuse it, and then look at how much C14 glucose you're forming in the liver. That would actually tell you what concentration of the lactate is being extracted by the liver, right?
Well, in people, we've gone C13, which is stable, non-radioactive.
Okay. Yeah. So C13 glucose production in the liver would give you that fraction. And of course, if you did this in direct calorimetry or indirect calorimetry, rather, you could measure the C13 CO2 coming out of the lungs, right?
Yeah, well, it gets tricky because measuring CO2 content is, really hard because most of the CO2 is carried as bicarbonate, carbamino. It's temperature dependent, pH dependent. We've done some of that, getting what's called the RQ, but we haven't done it as you described, Peter.
So based on Matt's work, though, you would say, look, when we infuse massive amounts of lactate into the femoral vein and then resample the femoral artery, the mass balance tells us it had to go somewhere. So it's either going, some of it's going to make glucose in the liver and some of it is being expired.
Yep. And again, in all our studies, we get oxidation is about 75 to 80%. So your initial premonition or premonition hypothesis about really we're talking about carbon flow, energy flow. The lactate can flow to around the body and be removed in diverse ways. Can be reconverted to glucose, which then gets oxidized. Or it can be just oxidized directly in the muscle or in other muscles. So for instance, we're working really hard. Maybe we see this in cross-country skiers. Our arms are highly glycolytic, release a lot of lactate. Our legs are redder, more oxidative. So here we are, we have poling, generating lactate, going into the arterial circulation, perfusing the muscle, fueling the brain, fueling the liver.
So that's very interesting, George. I had always assumed that the reason I could both see in myself and other athletes the highest levels of lactate following a swim, right? Like a 200 or 400 yard medley swim where you're doing all 4 strokes. It's a several minute effort. That was if the goal was how high can you make your lactate, that's the exercise to do it. Maybe followed by rowing. I just assumed it was because you had more muscles involved. I didn't know about what you just said. What you're saying is, no, the reason whole body activity would produce so much lactate is presumably you're using more muscles, but you have disproportionate type 2 fibers in the upper body relative to the lower body. Is that, did I hear you correctly in that regard? Yeah.
Ask somebody if they like changing a light bulb. I get tired right away.
That's so, how did I not know that? I mean, I feel like, what have I been doing for the last 30 years? Like clearly not learning.
You haven't been changing light bulbs.
That's such a good point. Yeah, the upper body really can get pretty fatigued relative to the lower body. Super interesting.
So if we look at fiber typing and, but we're evolved to use our arms in different ways. We use them at a low level. And at some point, maybe we want to talk about the size principle. So our type 1 fibers are easily recruited to low-level things, help us writing, taking notes. We're using type 1 fibers. But now, if we have to lift something heavier, now we need to recruit those type 2 fibers. And working overhead, we're using type 2 fibers, and we're really having clearance problems. So that's really fatiguing.
Let's talk a little bit about cancer. We alluded to it at the outset with the Warburg or Warburg effect, where cancer cells, seemingly in the presence of unlimited oxygen, still seemingly choose a metabolic pathway that avoids the mitochondria, although I'm going to come back and ask you about that now because we're going to call everything into question. But again, let's just go through the traditional thinking. Traditional thinking is you take cancer cells in a dish, you give them unlimited access to every substrate under the sun, and what do? They don't want to use fatty acids, they just want to use glucose, and they just want to make lactate. I know that the first hypothesis put forward there was, oh, well, cancer cells must have defective mitochondria. That's why they can't use anything else. And that's why they have to make so much lactate. That hypothesis doesn't seem to be the case. And it seems that there are other reasons. Famously, Lou Cantley, Craig Thompson, and I think at least one other colleague wrote, it was Matt Vanderheiden, if I'm not mistaken, that, well, the cancer cell is not optimizing for ATP, and it doesn't care that it's being inefficient in making lactate. It's optimizing for cellular building blocks because it's a cell that has to replicate without stopping. And that's why it's doing that. It's going down the lactate pathway to generate more carbon, nitrogen, whatever else it needs to actually build a cell. Tell me a little bit now about where your discoveries kind of fit into this hypothesis around why a cancer cell would follow the principle of the Warburg effect.
Yeah. Well, maybe that's a Nobel Prize, right? Understand that? Because
yeah.
I do, to rephrase that, I think the answer has been staring us in the face. Cancer is a problem of glycolysis, unrestrained glycolysis. And Ennio and I have some papers together. And in fact, he was kind enough to put my name on his most recent paper, which is now being reviewed for publication and has to do with the expression of certain glycolytic enzymes. And I don't want to spill Ennio's beans here about this. It has to do with the expression of glycolytic enzymes. And it looks as if that in all the various stages of cancer progression, lactate stimulates those. So, and Ennio is now looking at sort of the mitochondrial basis for that. So to repeat what you said, cancer cells do have mitochondria. We've seen that, other people have seen that, and they're capable of oxidizing different substrates, including lactate. But the lactate is generated, the high lactate production seems to stimulate a lot of things that are untoward in cancer. And one of the papers that Ennio and I first wrote was to look at all the adaptations in muscle, the training, and look at where cancer cells differ from the norm, and then look at those points of difference between training and cancer. And it has to do in part with lactate clearance. So those cancer cells do generate a lot of lactate, and the lactate is injurious in those cells.
So, it would be easy to listen to that statement and say a cancer patient should never be exercising, but and that might be one implication, although another implication might be cancer patients need to be exercising because they need a sink for all that lactate. Yeah. So which of those two do you think is more accurate?
So I used to believe the first one. Oh my gosh, we don't want to generate lactate. But then we thought more about it. Well, lactate's low because you clear it. And when you do regular exercise, you increase your clearance capacity. And so in that sense, if lactate is carcinogenic, by removing it, you lessen the chance for carcinogenesis.
Yeah, I mean, that's just simply kind of remarkable statements, right? I mean, if, first of all, that lactate is carcinogenic is kind of remarkable. And then it feeds to the difference between concentration and flux or flow. This is the most, I think in physiology, one of the hardest things for people to wrap their mind around. I'll give you another example, but it's something near and dear to my heart, right? Which is you look at intramyocellular fatty acids. Why is it, I mean, you know the answer, but I'm leading you down the path for the listener. Why is it that both the best athletes in the world and the most metabolically unhealthy people with type 2 diabetes both have high amounts of intramyocellular fat?
Yeah.
Well, of course, the difference is in the person with type 2 diabetes, it's static, it's stagnant, it sits there, and it is one of the causative drivers of insulin resistance. Yet in the athlete, it's just it's a carbon flow. It's moving. It's not, it's the difference between a stagnant pond and a flowing river.
Yeah.
And I think we get into this trap with lactate, don't we? Where we measure concentrations and we just assume high is high, low is low, high is bad, low is good. But we can't measure flux without, the complex instrumentation you use in a lab.
Yeah, that's true. And just to elaborate more on the marathoner paradox, if you do an EM and you find a mitochondrial network, you'll see a fat globule right next to it. So the potential for fat oxidation is great.
Yeah.
In our work, we've done some MRS and MRI, and we've looked at athletes, and they don't use much fat during exercise. But in the recovery period, when glycogen is low, that's the period of fat burning. So those fats there are prepositioning fuel supply in recovery when glycolysis switches off and people start to relax. So you're right about this whole idea of flux. Also in diabetes, glucose is high. Why? Was it produced too much or not cleared?
Right.
Well,
yeah.
It's
a great point. Yeah.
So that's easier to explain with glucose than with lactate. People more readily understand the dynamics of appearance versus disappearance, and the level is informative, but it's not the whole story.
So we've talked a little bit about, quite a bit about lactate in athletic performance. I have a much better understanding of that. You've talked about something very, very tantalizing with respect to brain health and TBI, and I'm very much hoping that this is being investigated. I mean, again, TBI is something where fortunately people are so much more aware of it today, but yet we still seem relatively poor in therapies. And if we had a metabolic tool to aid following a concussion. I mean, imagine if there was a concussion protocol that said every time a person got a concussion, they were to receive intravenous lactate, for X number of consecutive days, 4 hours a day at 4 millimole. Again, very testable hypotheses here. It's a little frustrating to think that this type of work isn't being funded. Given, heck, I would have the NFL Players Association be, look into this, right? Because you clearly have a high volume of individuals who are susceptible to concussions, and it would be easy to test that. We've talked a little bit about the role of lactate in cancer, although we'll save that for maybe the next time I have Inigo back on and let him be the one to talk about that. But the big takeaway there is, yes, lactate may be carcinogenic, but the bigger problem is not the accumulation of lactate. It's the accumulation of lactate in the absence of an effective clearance mechanism. And if one thing has become demonstrated over and over in our discussion today, it is that if you want to increase lactate flow and you want to increase lactate clearance, you must exercise.
Yes.
Are there other disease states besides these conditions we've discussed where lactate plays an important role in the pathophysiology?
Well, you suggested earlier on brain health, dementia, Alzheimer's. So it's really looking at exercise as protective, not just card game kind of mental exercises, but physical exercise. And people talking about brain blood flow and the delivery of substrates. And in fact, some people are talking about the role of lactate in stimulating neurogenesis and the dentate gyrus looking at development of new brain cells, which is which used to be a really heretical idea. The original idea was that when we're born, we have a certain number of brain cells. Now we know that there's a turnover of brain cells and they're renewed. And we know that the problems can occur when the progenitor cells are damaged or injured or not stimulated in some way. So I think there's a big future for investigators to be working in the field of physical activity and aging and the health span.
We talked very briefly about the role of lactic, of lactate specifically as a precursor or a canary in the coal mine around sepsis.
Yeah.
Do you believe that is still a valuable tool?
Oh, yes, definitely. But so to follow Bellamo's argument, okay, show me where there's an anoxic area in your patient. He challenges his colleagues. Show me where there's hypoxia. And so then the attitude becomes, well, it's not the cause, it's a response. And it's a strain, and understanding stress and strain.
Sorry, just to back up for a second. He's saying this to ask the question, if you're telling me that lactate is the response to anoxia or hypoxia, why, when we see lactate going up in a septic patient, can you not point to the area of anoxia? Is that the question he's posing?
Yeah.
Okay. And then tell me what the response is to that
I
question.
don't know what the response is to that. Nobody can identify it. But my own, and I've written about this, anticipating this kind of general question, where is this lactate coming from? I think it might be coming from the gut, personally.
That's what we were taught, George. When I was in the ICU, we were taught when you see these rising lactate levels in patients, it is hypoperfusion of the gut. Now, okay, so I measured a lactate level in a patient and it's up to 10 millimole. That's bad news. But am I supposed to take that patient to the operating room and look for ischemic bowel? There's still a bit of that tells you that's a lot of smoke, but it doesn't tell you where the fire is.
Yeah.
Even if you believe it's a gut perfusion issue.
Well, I think part of it is because the microbes are producing racemic lactate. They're producing L-lactate and D-lactate. And most of our body runs on the form of lactate that's identified as L-lactate. But I think in sepsis, there's a lot of D-lactate going on that is formed in the lower bowel as opposed to the upper bowel.
Is that how easy is it to distinguish between those two? What it's been so long since I've done organic chemistry, I don't remember how we distinguish. I understand the difference between a D and an L, but I don't remember how one measures it.
Oh, so most of all the analyzers we have, hospital elsewhere, measure the L form, and these are I'm holding up my hands here on purpose to say one is the mirror image of the other, and the L is the form we usually make and utilize. But if we make this other form, now we have this stuff which is neurotoxic and pro-inflammatory. And I think that in large part, people can't really see the extent of the lactatemia that occurs in sepsis.
Wait a minute. You're saying that when we measure the 10 millimole in the septic patient, the 10 millimole is only the L-lactate concentration because that's all the assay measures, but there could be 20 millimole of D-lactate there that is actually causing a problem.
Yeah.
How could we confirm or refute that?
Well, we would need to have a special, I think there is, this is your field, not mine. There's a term D-lactic acidosis. And we know D-lactate is toxic. So now we would need a special kind of analyzer to detect it. And that's not the common analyzer that's around. All the analyzers, the blood gas analyzers, the portable devices, most of the enzyme techniques, Um, the the recipe in Bergmeyer's textbook is for L-lactate.
Do you have the ability in your lab, if you wanted to measure D-lactate, to do so?
No, in the past I've submitted some grant applications with clinicians who would want to do this, and we haven't gotten very far.
Interesting. So where do we derive the belief that D-lactate is neurotoxic and pro-inflammatory?
Yeah, because if you give it, it is, and when people can measure it, it's associated.
Interesting. So your hypothesis is that the bacteria are making the lactate, and they're disproportionately making the less desirable form of it, and that the L-lactate, that which you're actually measuring, is probably not causing any of the problems associated with the sepsis. It's just it's telling you that something else is going on.
Yeah, and those microbes will make lactate regardless of the presence of oxygen. So if you were saying, well, his gut is ischemia, and you mentioned it would be very hard to demonstrate that, and you wouldn't want to actually maybe bothering to measuring it if you have a microbe that is the site of this lactate generation.
So what is the most interesting question that you are asking today that you still don't have an answer to in your mind with respect to lactate metabolism?
Yeah, thank you for that. Our most recent paper touches on this. So for 100 years, everybody, including us, have been thinking about muscle and related tissues that can use lactate, but it's all been a muscle thing. So we did a very simple test. We used our isotopes as we usually do. We had aboard carbon-13 labeled lactate, and then dihydroglucose and D5 glycerol, so we could measure lactate, glycerol, and glucose all at the same time. And then we gave people an oral glucose tolerance test. And the first thing that came out in the arterial blood, and this is arterial blood, not venous blood, the first thing that came out after taking glucose is lactate. So there's an enteric glycolysis that takes place. And this is the way the body participates in distributing carbohydrate energy to make lactate. So this just changes our mind completely.
But sorry, George, did we not know before this that when you consume glucose, lactate goes up?
We know that, and nobody would understand why. It's part of the lactate shuttle. I presented this in our most recent studies last year at the American Diabetes Association. There was a doc there from NIH, and he said, well, we feed carbohydrate, we get 2 millimolar lactate. So what's the deal? That's the way the body's working. In sports, we would say it's hiding the ball. In baseball, we hide the ball. In football, we try to hide the ball. Here, the body's trying to minimize the glucose load, but still deliver carbohydrate energy. And it starts with the enterocytes in the gut. So there are plenty of studies where people would incubate enterocytes under air, give glucose immediately. You have lactate.
And just give me a sense of scale, right? So when you give somebody an oral glucose tolerance test, this is 75 grams of glucose. You gave a standard dose, I'm assuming?
Yeah.
Okay, so plasma glucose in these subjects will easily double, right? It'll easily go from 75 milligrams per deciliter to 150 milligrams per deciliter, correct?
Yeah.
And lactate might double, maybe go from 0.6 to 1.2 millimole, correct?
Correct.
From a mass balance perspective, I'm not smart enough to remember how to do this. Can you remind me how much carbon went in each of those two paths?
Yeah, so good point. We're just talking about the concentration, but earlier we talked about the flux.
Yeah.
Okay, so So it looks like the liver is really, really important in this whole thing. And we did touch on the liver and its importance. It's really underestimated, and you're asking about what I think I want to do next is to really explore this problem which you are articulating. How does the body shuttle carbohydrate energy? So you said the blood glucose will rise and it will double, but it doesn't get that high until 30 minutes after the test. Whereas if I give the glucose, the lactate is spiking in 5 minutes, reaching a peak at 15 minutes, then subsiding, and now the glucose is starting to become the carbohydrate energy form.
But just so that listeners understand something you and I take for granted, when a person's blood glucose goes from 80 to 150 milligrams per deciliter, that's still a trivial amount of absolute glucose difference concentration. It's a difference of 5 grams of glucose in the entire circulation that would explain that delta. You still gave the person 75 grams. In other words, we have to account for 70 more grams of glucose. And my thinking was that most of that's in the muscle, right? That's when we do oral glucose tolerance tests on everybody, George. I mean, we are, we just really believe that is a great functional test of glucose disposal. But truthfully, we're not measuring lactate when we do this. Maybe we should be, but we're basically asking the question, how sensitive are your muscles to insulin, and how much of a reservoir do you have to dispose of glucose? Because we're also measuring insulin every 30 minutes as well as glucose. But now I'm wondering, because we haven't measured lactate, there's another pathway we're not accounting for, which is how much of the glucose are those enterocytes turning into lactate as an alternative fuel source?
Yeah, so that's the first part of what happens. We saw it, and we were lucky to have arterialized blood, so we could see the spike in lactate that comes out after taking glucose, way before the glucose starts to rise. And then from our isotope technology, we could see that when glucose is rising, it's giving rise to lactate. That's been seen before. It's called the indirect pathway. But to go back to an earlier point you raised about the importance of the liver, and this is in our paper we referenced the work of Stender, who gave 13C glucose in an OGT. The liver picks up most of it. And the liver is basically sequesters about 80% of the glucose load and then doles it out over time. And it starts to release this glucose after about, I'm trying to remember their study, 30 minutes. Meanwhile, lactate has a big role. It plays a role. And meanwhile, the glucose is still in the liver. And now it starts to be doled out. It's being released as glucose. And that's getting converted to lactate in the muscles. And that's what's called the sort of indirect pathway of glucose metabolism. So the liver is really key. So what I would hope to be able to do in the near future is to really revisit all these dietary nutritive aspects of, okay, glucose gets taken up, glucose is taken up, made into lactate. Well, what if we have fats there? Like a real meal. Not just an OGT, maybe a meal tolerance test. We would do this. A version of this was done by somebody named Schlicker in Germany, and they did this really incredible study. They did make a mistake because they forgot about the liver. They grew grain in a high carbon 13C O2 environment. And plants, I think most people know, take CO2 from the air when they make sugar. So they did an oral glucose tolerance test with 13C, and also they harvested this grain, and they did a meal test. And they made porridge out of this stuff, and they looked at the appearance of lactate and glucose in the blood. And they saw the same thing we did. Right away, there's a spike in lactate. And they said, well, lactate's the whole story. But they forgot about the liver.
So you're saying in a standard oral glucose tolerance test, your belief is that most of the glucose that is being disposed of is actually being disposed of initially by the liver, and then the liver starts doling that back out, the muscle picks it up, and then the muscle is your secondary production of lactate is by the muscle. Your primary production is by the enterocyte on immediate. And then that's why you get two peaks of lactate, right? You get the first fast peak in response to the enterocyte making lactate, and then you get a second delayed, slower peak when the muscles get the glucose from the liver and start making lactate.
Yeah. And one of our core investigators is Umesh Masharani. He's a diabetologist at UCSF. And he said, well, maybe that's how metformin works. So for our listeners, your listeners, metformin is the most popularly prescribed drug for high blood sugar. And one of the concerns is that when you give that drug, lactate rises. And Umesh is very comfortable saying, well, the body's making lactate. So metformin is encouraging enterocytes to make lactate. That's why the lactate's high, and that's a good thing.
Very interesting. As you know, there's a body of literature suggesting that metformin may enhance exercise performance. May impede exercise performance. And again, the problem with metformin is despite the fact that this drug's been around, it's almost as old as God. It seems to have so many points of action that it's very difficult to know what it's doing or how much of its net outcome, which is, reducing hepatic glucose output, can be attributed to what, right? So I guess the conventional thinking on metformin is it's inhibiting complex 1 of the mitochondria, correct?
Mm-hmm. Yeah.
And if you inhibit complex 1, you're activating AMP kinase. That should reduce hepatic glucose output, correct?
It does that.
But it's always been, it's as sure as God made little green apples, anybody on metformin has higher lactate levels.
And that's a bad thing, or it was a bad thing. Maybe it's a way to deliver carbohydrate energy.
Well, yeah, I had always assumed that the doubling, at least doubling, if not 3x increase in resting lactate levels in the case of metformin were due to the complex 1 inhibition, right? That's, just, again, obviously a maybe naive assumption, but it was, hey, if you're inhibiting the electron transport chain, of course you're going to have more lactate. But that may be true and unrelated.
That's why I want to give carbon-13C lactate or carbon-13C glucose and look at the appearance of carbon-13C lactate in the blood and do the quantitation you described. Where does the glucose go?
How much would it cost to do the definitive experiments on the full flux disposal of lactate? This doesn't strike me as staggeringly high amounts of money to do this type of research.
We could start very well with an R01 basic research grant. That's $2.5 million.
Yeah.
That would be a start. That's just to handle the glucose. But the real interesting stuff would be when glucose appears as it does in a meal with other things.
It would be interesting. Have you done the experiment you just described, the OGTT experiment, to individuals both on and off metformin? It would be interesting to see the difference in lactate production in those two individuals. And it would be interesting to also see if there was a way to quantify this enterocyte production.
Yeah, Dr. Masharani and I want to do that. So with metformin, if we give metformin and there's an increase in lactate in the plasma, is that due to production outstripping removal? Or are we actually increasing the oxidative disposal of glucose? Or is the glucose high because of increased gluconeogenesis? We could answer all of these things with our combination of tracers we use.
Again, let's go back to conventional wisdom. What were we taught in medical school and residency? Be careful of metformin because you increase the risk of lactic acidosis. So a person on metformin is at an increased risk for lactic acidosis if they get dehydrated, if they get contrast in a CT scan. When viewing that concern through the lens of what we've just discussed, does it make sense?
Well, caution is always advised. First, do no harm, right? So when we're prescribing this medicine, we don't know if it increases lactate production or inhibits disposal.
Right, but let's go back to the very beginning, right? Which is, just because you increase lactate production, does that mean you're causing acidosis?
Well, that was another important consideration. Lactate rises. What's the change in pH?
Yeah, what happens when you take those subjects, the TBI subjects, and you clamp them at 4 millimole? You said, if I recall, there was no change in sodium, but I think you also said there was no change in pH.
Oh, there's a slight alkalosis.
Slight alkalosis. How much? 7.38 to what?
7.38 to 7.35.
Well, that would be a slight acidosis.
Excuse me, just the opposite way. 7.4.
Okay. And the colleagues that you referenced in Germany, I think, or Switzerland, who were taking people up to 8 millimole, were they seeing an acidosis?
They did not report it.
Okay, so does that mean it's possible that high levels of lactate do not materially alter acid-base physiology?
Well, in your experience, is sodium lactate given in metabolic acidosis? Sometimes it is.
Yeah, but the lactate concentration is very low in that setting. Like, it wouldn't be as high as what the examples you're citing are much better examples to ask this question because of you're clamping people at a really, really high lactate that you just don't get to. But again, it seems to me that if what you're saying is correct, George, there's a lot we're misinterpreting from, for example, sepsis literature, right? Where you get that patient in the ICU who's got high lactate. Well, they also have a low pH, but those two things could be driven by different processes.
Yeah, exactly. So when we addressed this earlier, I think if you see a low pH, yeah, you need to do something. If you see a high lactate in the absence of a change in pH, I would be very inclined not to do much.
Very interesting. You've given me and everybody listening a lot to think about here, George. So it seems to me that understanding the full flux, the full mass balance of lactate, both exogenous and endogenous, is a necessary step to fulfill our understanding of metabolism in a more complete manner, correct?
Yeah, thank you. I think so.
All right.
Oh, and you mentioned endogenous versus exogenous. So when we exogenous means we're going to infuse lactate or put it in the body some way. Well, I learned in organic chemistry the salt of an acid is a base. So it's not unexpected that when you give it, pH will rise slightly. And maybe part of that also is sodium. What does it mean to use this exogenous stuff? So lactate is distinguished from pyruvate, and lactate is reduced it has more hydrogen on it. There's one more hydrogen in pyruvate. So that that keto bond on pyruvate, the double bond oxygen, becomes hydrogen.
Yep.
So it's more reduced. Now, when you start putting in this reduced equivalent into the blood, it's going to go around the whole body and change redox in a number of tissues. All the tissues, basically, to which it's going to, where the lactate's going to go. So lactate is a powerful signal, and it works in diverse ways to activate various pathways, including by changing cell redox.
What does lactate do in terms of gene expression? We haven't talked about that, but given how potent a signaling molecule it is in both metabolism directly and vis-a-vis redox, what do we know about other forms of signaling and expression of genes?
So there's a new field now. So we used to think genes are regulated in part epigenetically by acetylation or methylation. Now we realize they're also lactylated. So we've done some of those experiments here in our lab. We haven't published yet, but the lactate is a predominant metabolite, and it can bind to genes, and it can affect gene expression.
Meaning it can covalently bind?
Mm-hmm. Acetylation, methylation, lactylation. Yeah. So that's actually a term. And I was going to compliment you on your reading of the literature, because you can look that up in PubMed, and you can see that people are starting to look at lactylation of histones by raising lactate.
So it's not through histone acetylation. It's direct lactate binding.
Yeah, and it's called lactylation.
Yeah.
Dr. Attia, you've got us up into the stratosphere here of where the science needs to go. Starting with the premise, exercise is healthful. How can it affect the body corpus, promote healthful living? Well, possibly in part by lactylation of histones, promoting mitochondrial biogenesis.
It's very interesting because we've talked about all of these benefits of exercise, right? We talk about how, my friend clearly has more mitochondria than I do, and he has more MCTs, and he's so much better at clearing lactate and all of these things. But of course, what we're missing in that is the how and the why. Why is he doing that? What is it about his training stimulus that does that? And what you're suggesting, at least as a hypothesis, is what if the lactate itself is signaling the gene expression that leads to the more favorable phenotype seen in the athlete?
Yeah, well, with Takeshi Hashimoto, we published a paper. If you just take muscles, put them in muscle cells in a dish, you add lactate, you activate 500 genes.
But here's the thing. There has to be something, if I'm just thinking about this perhaps a bit too quickly, I would have to believe it also must involve something favorable with consumption. It can't just be in other words, I have a hard time believing if you took my friend and you took me, right? Mm-hmm. And you would argue based on his training and based on my training, I'm on a bike 3 or 4 hours a week. He's on a bike 15 to 20 hours a week. He's clearly making more lactate in any given week than I am, and he's clearly using more lactate in any given week than I am. But if you came up with an experiment that you imagine you could do this, where you could pair feed us lactate, okay? So in other words, for every millimole of lactate he produces endogenously, you exogenously deliver the same lactate to me. I still don't think we'd end up the same, even though we have the same input of lactate, because he's using it during exercise, whereas I'm sitting around on my butt while you're giving me all of that lactate. Mm-hmm. So it's hard for me to imagine that lactate by itself would be the signal. I have to think there's something associated with the benefits of how lactate is consumed during exercise.
So yeah, this is of interest in the literature now. People are doing lactate clamps on people and looking for increases in mitochondrial protein expression.
And what are they seeing?
There's sometimes yes and sometimes no.
This sounds a lot like amino acids.
It has to do with the endogenous versus the exogenous, because you get completely different signals. So it's the endogenous lactate, when it's high, seems to stimulate mitochondrial biogenesis rather than just infusing it.
Okay, but why would that be?
Well, a lot of these pathways are redox sensitive.
Okay. So I want to make sure the listener understands that. That's a very important point. Because it's redox sensitive, that's just fancy speak for saying it depends on the amount of protons or pH balance of what's going on. And if you just give somebody lactate without actually creating the slight alteration in pH that is naturally going to be accompanied by exercise, you don't reap the benefits. Whereas if the lactate is produced in concert with exercise, you get the lactate, but you also get the pH perturbation that is the key to unlock its potential.
That's a very good explanation of what I'm seeing. This is, again, work of others who are really serious scientists. And I think it has to do, the mixed results they are getting, it depends on whether it's exogenous or endogenously produced lactate.
So, of course, it would beg a question, which, again, if I were czar, George, if I were in charge of NIH funding, I'd be throwing much more than just a paltry little R01 at this, because I think it's such an interesting question. But going back to the TBI example, I would want to study as follows, right? I would want to take a whole bunch of people with traumatic brain injuries or concussions. You give one, so you got a placebo group. You've got a group where you just infuse more glucose and insulin, intranasal insulin and glucose, right? Another group where you just infuse lactate. You take them to equal concentration of lactate glucose, so you take them up to 5 millimole of both. Then you have another group where you do that, but they exercise 2 hours a day, steady state, like zone 2, just enough to get their own endogenous lactate up to about 2 millimole, and then, get that clearance. Because you might argue that it's that exercising group that's also being given exogenous lactate might actually have the best outcomes because they're getting the redox potential as well as the lactate.
Yeah, so we thought about this. So with a TBI patient, it's probably not in the cards for them to doing any exercise. But what about functional electrical stimulation of a comatose patient?
Yeah, although I know a lot of people that have had TBIs. I don't think they'd be up for strenuous exercise, but wouldn't they be up for even, just...
Oh, you're talking about mouth, well...
Yeah.
The setting was,
Sorry, yeah, I mean like somebody who's had a concussion, but they're still functional, but they're suffering sort of the negative consequences of it, yeah.
Well, I think you would want to encourage mild exercise on these people.
Yeah.
I was talking about the
Yeah, someone who's comatose with a significant CNS injury, yeah.
Well, how do you raise lactate in them endogenously? Mild electrical stimulation.
It all comes back to Meyerhoff, right?
Well, that's the beginning.
Yeah. We're back to frogs with electrodes.
Well, we're beyond frogs with electrodes. And now I think we were understanding that it's just not a muscle thing. It's the whole thing. And there's glycolysis going on simultaneously. And to get back to our story about the muscle fibers, a lactate producer, a lactate consumer, exchanging chemical energy, or our studies on healthy people with heart. When we're exercising, our muscles hard enough are going to release lactate, but it's now the favorite fuel for the heart. Studies that Hashimoto did of executive function. He did these with Neil Secker in Copenhagen. He give people tests, standard cognitive tests. Then they exercise and build up their lactate. They score better. Then they recover, their lactate comes down. They go back to their basal scores. It's brain fuel. So think about the PE class, getting kids out to run around. That is not blowing off emotional energy. They're going to fuel their brain for the next hour or so.
Yeah, it's so interesting because you just have to believe that there are too many factors in there to identify the amount of contribution of each. For example, we all know that when you exercise, BDNF goes up and clotho goes up, and all of those things have pro-cognitive benefits as well.
Yeah.
So it's probably difficult to just assign all of the benefit of exercise. There's a clear, obvious benefit between exercise and cognition. And what it sounds like is that there are many biochemical pathways that feed that, and lactate may indeed be a preferred energy source.
There's one study where lactate was infused and BDNF went up.
Interestingly, I'd love to see. I wonder if anyone has ever looked at lactate infusion and clotho concentrations.
I don't know.
Yeah. Well, George, this has been very interesting and illuminating. I think that it's safe to say that so much of what I think many others listening thought we knew about lactate was at best incomplete and in some cases incorrect. So I'm glad we have finally had a chance to sit down and go through some of this really incredible work. I do hope that somebody in a position of funding is listening to this and realizes that for a relatively small sum of money, relative to the type of money that's thrown at a lot of biomedical research, we could really still answer some fundamental questions about the fate of lactate and the interplay with glucose, especially and the role of the liver and the enterocytes. So anyway, I'm hopeful that with the reach of this podcast that someone's listening and they think, yep, this is a good use of funds.
Thank you, Peter. I agree completely. And thanks for the opportunity. And again, my physician friends listen to you more than they me. And now that they listen to you, they'll listen to me.
Now they're stuck listening to you. All right. Thanks, George.
Cheers.